A More Threads full-function GPU die sits on the table. The package is standard, the bracket carries display outputs, and the company's own materials describe a single piece of silicon that renders a three-dimensional scene and trains an artificial intelligence model without handing off work to a second chip. That surface description is accurate as far as it goes, and it does not go very far. The deepest layer of this particular die does not reveal an engineering preference for unified architecture. It reveals the outline of a specific set of restrictions, each one legible in a different region of the substrate, and together they explain why this chip looks exactly the way it does and not some other way. We open the package first, then split the die into its functional regions, then follow the memory subsystem through the negotiation it must make between two structurally different workloads, then reach the buried constraint at the level of packaging infrastructure, where the architecture's true origin becomes readable. Removing the cooler and lifting the package reveals the first piece of evidence before the die is even measured. The bracket carries display outputs, and a pure artificial intelligence accelerator would not carry them. NVIDIA's data center accelerator line removed display outputs years ago because the connectors added cost and weight without contributing to the training throughput that data center customers purchase. More Threads retained them. The teardown observations available from domestic market cards confirm their presence on products the company positions for both graphics workloads and artificial intelligence training. Those connectors are not incidental to the design. They are the outermost record of a market decision. More Threads entered the Chinese domestic graphics processing market at a moment when NVIDIA's consumer and workstation cards had already established the assumption that a graphics processor renders images to a display. Launching without display outputs would have required buyers to accept a new product category, a dedicated artificial intelligence accelerator, at a moment when domestic procurement channels for that category were not yet established at scale. The connector on the bracket is a trust signal addressed to a procurement officer before it is a technical specification addressed to an engineer. Moving inward past the package to the die itself, the outer geometry reflects a unified shader architecture, meaning the same execution units handle both graphics shading instructions and general-purpose compute instructions, including the matrix operations that dominate neural network training. More Threads' own technical materials describe this structure, and it is the same architectural principle that NVIDIA adopted during the transition to its unified compute environment beginning roughly 2 decades ago. A unified execution fabric is the only architecture that makes a dual-purpose claim credible at the die level. Separate fixed pipelines for graphics and compute would have placed 2 distinct execution fabrics on the same substrate, competing for die area, power delivery, and thermal budget without sharing either. The unified approach allows More Threads to state accurately that the same transistors capable of shading a polygon can also perform a matrix multiply. Whether those transistors perform either task at competitive efficiency is a question the outer geometry cannot answer. That question requires opening the specific regions dedicated to each workload. Cutting into the graphics-specific region of the die, the teardown identifies fixed-function rasterization hardware, the blocks that convert 3-dimensional geometry into a 2-dimensional image by performing geometric transformation in silicon rather than in programmable shader code. This hardware is not reconfigurable. Die area committed to rasterization cannot be reassigned to matrix arithmetic when the chip is running an artificial intelligence training job. The fixed-function rasterization blocks sit on the substrate doing nothing during a training run, consuming area that a purpose-built accelerator would fill with additional compute capacity. More Threads' product positioning in the Chinese domestic market includes workstation graphics cards competing with older professional graphics lines, which establishes that the rasterization pipeline is not vestigial. It carries revenue. The decision to preserve it on a die also carrying matrix acceleration units was made at the business level before it was made at the engineering level. A company that abandoned graphics entirely would have lost the domestic consumer and workstation revenue streams that fund operations between the large capital raises that advanced chip design requires. The rasterization hardware is expensive in die area, and it is the price of remaining viable in the near term while building toward competitive artificial intelligence performance in the longer term. Moving into the compute fabric, More Threads' technical documentation describes matrix acceleration units designed to perform fused multiply-accumulate operations at the precision formats used in neural network training, including the lower precision arithmetic that reduces memory bandwidth pressure during large model workloads. These units exist on the die because training a neural network on general-purpose shader cores without dedicated matrix hardware is possible, but carries a throughput penalty severe enough to make the chip unconvincing as a training platform. The structural fact exposed by this layer is not the presence of the matrix units. It is their relationship to the rasterization block sharing the same substrate. The two capabilities do not enhance each other. They compete for the same finite die area, the same power envelope, and the same thermal headroom. Peak matrix throughput on this die is constrained by the area the graphics pipeline occupies, and peak graphics throughput is constrained by the area the matrix units occupy. No independent laboratory has published a full methodology benchmark of this die's training performance against a major public model with results replicated by a third party. The performance figures in circulation derive from the company's own materials or from limited domestic technical reviews that have not been independently verified. The hardware is present. Whether it performs at the rates claimed remains an open question that the dissection cannot close. The memory subsystem is where the negotiation between the two workloads becomes physically measurable in a way that specifications make concrete. More Threads products have used graphics double data rate memory, the same memory standard found in consumer graphics cards, rather than the high bandwidth memory stacks used in NVIDIA's data center accelerator line. Graphics workloads stream texture data in bursts with high spatial locality, and graphics double data rate memory handles that access pattern adequately. Artificial intelligence training workloads shuffle large weight tensors across the memory interface with irregular strides and sustained high bandwidth demand. High bandwidth memory stacks deliver substantially more bandwidth per watt and per square millimeter than graphics double data rate configurations at comparable capacity. At the configurations relevant to large model training, the gap between the two memory standards is not a small percentage difference. It is measurable in hundreds of gigabytes per second, roughly the difference between a pipe-sized for a garden hose and one-sized for a drainage culvert. The More Threads die enters every training comparison carrying that deficit, and the deficit is not a design oversight. Graphics double data rate memory is produced at higher volume, is accessible without specialized supply chain relationships, and solves the graphics problem adequately. High bandwidth memory stacks require close relationships with a small number of suppliers, and those supplier relationships carry their own access constraints in the current export environment. The memory architecture of this die is a direct record of what the company could procure and what was sufficient for the market segment anchoring its revenue. The artificial intelligence training workload is the higher demand tenant on a shared interface sized for the lower demand one, and that ceiling is visible in every bandwidth figure the chip produces. The software stack that programs this die is itself a layer of the dissection, because silicon capability without software accessibility does not generate revenue. More Threads has developed a compute programming environment described in the company's own documentation as offering compatibility layers and toolchains intended to allow workloads originally written for NVIDIA hardware to run on More Thread silicon with modification. The degree of compatibility and the performance of ported workloads relative to native execution on NVIDIA hardware have not been independently benchmarked across a representative set of artificial intelligence frameworks. What is established is that the stack exists, and that it is actively developed. The structural cost this layer exposes is specific to the dual-purpose architecture. NVIDIA built its graphics driver stack and its compute programming environment over roughly 2 decades, with separate engineering teams and separate release cycles. More Threads is building both simultaneously on a compressed timeline with a smaller engineering base. The graphics driver must interoperate with game engines and workstation applications across multiple operating systems. The compute stack must allow artificial intelligence frameworks to schedule work on the matrix units and manage memory transfers efficiently. Neither stack can be neglected without losing one of the 2 revenue pillars the architecture was designed to support. The software layer is where the cost of the dual-purpose strategy becomes most visible. It is not twice the hardware engineering work, but it is something close to twice the software engineering work, and the team carrying that load is not twice the size of a team building for a single workload. Placing this die in the context of the Chinese domestic artificial intelligence accelerator market exposes something the die itself does not reveal. More Threads' choice to retain full graphics capability is not the dominant architectural strategy among Chinese semiconductor firms. Companies developing purpose-built artificial intelligence accelerators in China have made the opposite choice. concentrating die area, memory bandwidth, and software engineering effort on compute throughput by abandoning graphics entirely. More Threads occupies the minority position in its own domestic competitive landscape. The company's star market listing in December 2025 and the reported first quarter revenue growth of roughly 155% are the company's own figures and have not been independently audited. Read against the architecture, that growth figure is ambiguous in a specific way. It does not distinguish between revenue from graphics cards sold into a domestic market with limited alternatives and revenue from artificial intelligence training deployments. A single die strategy makes this ambiguity structural. The company cannot cleanly separate its two revenue lines in reporting because the product does not separate the two workloads in silicon. The full function die is a hedge as much as it is a technical achievement. A company that can only sell into the artificial intelligence accelerator market is exposed to every fluctuation in that market and to every competing product from domestic rivals who have specialized more deeply. A company that also sells graphics cards has a second revenue base that does not require winning on raw training throughput. At the deepest layer of this dissection, the die reveals a fact that no single specification sheet states directly. Advanced chiplet packaging, the technique that allows leading chip designers to disaggregate a large die into smaller tiles manufactured at different process nodes and assembled into a single package, requires access to advanced packaging infrastructure that China's domestic semiconductor supply chain has not replicated at commercial scale. A disaggregated design could have separated the graphics logic from the artificial intelligence training logic, allowed each portion to be sized independently for its workload, and allowed more threads to offer a dedicated artificial intelligence accelerator tile without carrying the die area cost of a full rasterization pipeline on the same substrate. More Threads has not done this. The full-function single-die architecture is not evidence that the company prefers monolithic integration as a matter of engineering philosophy. It is evidence that the packaging infrastructure required to do otherwise was not available on the timeline the company was working within. The floor plan of this die is not the floor plan the design team would have chosen in an unconstrained environment. It is the floor plan that was achievable given the manufacturing and packaging capabilities accessible to them at the moment of design commitment. The dissection establishes the structural logic of each layer, and it also has firm limits. More Threads matrix throughput and training speed figures derive from the company's own technical materials and from domestic reviews that have not been replicated by independent laboratories with published methodology. The teardown identifies the hardware. It cannot confirm that the hardware performs at the rates the company claims. The die photograph with annotated functional regions, block sizes, and precise area allocation that would allow a confident measurement of how the graphics pipeline and compute fabric divide the substrate has not been made public. The structural inferences drawn above are reasonable given the available architectural descriptions and product positioning. They are not confirmed measurements from electron microscopy or reverse-engineered circuit analysis. And the physical constraint that a monolithic die must serve two workloads within a shared thermal and power envelope means that peak performance on either workload is lower than what a die of equivalent area committed entirely to that workload could achieve. That ceiling is not a software problem. It is a physics constraint the full function architecture accepts as a condition of its own existence. The dissection establishes the structural logic. It cannot measure what a disaggregated version of this design would have achieved on training throughput, and it cannot confirm the throughput claims independently. What this die proves, examined as a complete object rather than a parts list, is that a semiconductor company designing under sustained supply chain pressure does not produce a smaller version of what an unconstrained company builds. It produces a different shape entirely. More Threads did not build a diminished version of a leading data center accelerator. It built a chip whose architecture encodes, layer by layer, the specific set of conditions that surrounded the design team at the moment the floor plan was committed. The rasterization pipeline is present because the company needed graphics revenue to remain solvent long enough to compete in artificial intelligence. The unified shader fabric is present because separate fixed pipelines would have consumed more die area than a monolithic process node permitted while also supporting the matrix units. The graphics double data rate memory interface is present because the alternative required supplier relationships the company could not form. The full function single die architecture is present because chiplet disaggregation required packaging infrastructure that was not accessible on the relevant timeline. Every layer, once opened, points to the same origin. The restriction designed to hold this company back is the blueprint the company built from. The next object worth opening is the one that made the opposite architectural choice, a Chinese artificial intelligence accelerator that abandoned graphics entirely, concentrated every available transistor on matrix compute, and now competes on raw training throughput without a graphics revenue floor beneath it. If you want that dissection next, name the chip in the comments. Subscribe to follow this channel's dissections of the hardware reshaping the map of where computation is made.